Whoops. Getting the little color wheel thing going on here. That's not what I want. Okay. Where have you seen that before? No. So funny, though. That's what I did this morning. I derived the quadratic formula. Okay. Yes. This is the slope of a tangent line. Correct. At a point A of a function f of x. Correct. Good. This is the slope of a tangent line at point A of a function x. Okay. Now, it turns out that slopes of tangent lines are super useful in the world because I mentioned this at the very beginning of the course. Slope of a tangent line of a function tells us about the instantaneous rate of change at that function at that particular time. Okay, and so we actually call this thing a derivative. Okay, we call the slope of a tangent line at a particular time the derivative of a function. So this slope is called the derivative at point A of f of x. Okay, f prime of A, that's how we would say it out loud, is the derivative of the function at point A of f of x, and that represents the slope of the tangent line at that specific point in that function. Okay. Now, how do we find this? Well, luckily we've already done that. Okay, we already did that last unit, right? We use limits. Okay, so for example, if we wanted to know what is the slope of the tangent line for this function at this specific point, okay, well, the derivative of the function x, where x equals 2, is the limit as h approaches 0 of f of 2 plus h minus f of 2 over h. Okay, now previously we just called this the slope at point 2. This is now called the derivative of the function f of x where x equals 2. We are renaming the slope of the tangent as the derivative of the function. Okay, and let's go ahead and find this. So firstly, f of 2, let's just figure that out. Okay, so f of 2 is 2 squared minus 3 times 2 minus 4, and that's what? 4 minus 6 is negative 2, right? Minus 4 is negative 6, I think. Yeah, negative 6, okay? So this piece is negative 6. So we're going to get 2 plus h squared minus 3 times 2 plus h minus 4 minus negative 6 over h. Okay, and that is, all right, well, 2 plus 8, or this piece is 2 plus h squared is 4 plus 2h plus 2h is 4h plus h squared. Minus 6 minus 3h minus 4 plus 6. Over h h. Oh, I dropped the limit. I don't want to do that. Limit as h approaches 0, sorry, equals the limit as h approaches 0. There we go. That's better. Okay, now in the numerator, there's some stuff that equals 0. So for example, 4 minus 4 is 0, so that's gone. And then negative 6 plus 6 is 0, so that's gone. Okay, so that's nice. And then in the numerator, I've got what? 4h minus 3h is just h plus h squared, right? Over h. Ah, I did it again. Limit as h approaches 0. And so now we can factor out an h in the numerator, which is great. H times 1 plus h over h. Those cancel. And now we can sub in a 0 for h. And we get that f prime of 2 is 1 plus 0, which is 1. Okay, so in other words, the derivative of the function f of x when x equals 2 is 1. Okay, so there's a number of ways that we can interpret this. Okay, the derivative of f of x when x equals 2 is 1. The slope of the tangent line of f of x when x equals 2 is 1. Or of f of x when x equals 2 is 1. Okay. F prime of 2 equals 1. These all sort of say the same thing. Okay, so this is not much new, but we're introducing some new vocabulary. Instead of talking about just the slope of a tangent line, we're talking about how we're going to call that the derivative of the function. Okay, now it's kind of annoying to have to do that for every single a value. Every time we get a different a value, we have to do that same process over and over and over again. So if I had that same previous function, f of x equals x squared, I can't remember what it was, minus 3x plus 4 or something. If I gave you a different a value of a equals 5 instead of 2, got to go through the whole thing again. And if then a equals 10, got to go through the whole thing again. That's annoying. So instead, what we're going to do is define a function, f prime of x, which is the derivative function. And this is a generalization. So if we can come up with the derivative of f of x, f prime of x, and we can write that as a function, we can just use that derivative function for any x value we want. We don't have to now do that whole limit process every single time we get a new value of x. And so that's what we're going to do today. Okay? So, for example, and basically to do that, by the way, instead of having f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a over h, we're going to look at f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. So it's the same sort of thing, but we're not going to be dealing with specific numerical values here. We're going to be dealing with the function itself. Okay? So, for example, use the derivative of f of x equals 6x squared to find f prime of 1 and f prime of 2. Okay, so what we're going to do first is we are going to find that derivative function. Okay, the general derivative function. And then once we have that function, we can use it to find the slope of the tangent line, or the derivative of the function, at any x value that we want. Okay, so here's how it's going to go. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, that's going to equal the limit as h approaches 0 for this particular function, which is 6x, f of x equals 6x squared, 6 times x plus h squared. Okay, because for this first piece, we need to replace the x with x plus h, minus f of x minus 6x squared over h. Okay, now this piece, just do that off to the side, is x times x is x squared plus xh plus hx, or plus xh, plus h squared. So that's x squared plus 2xh plus h squared. Okay, so that is going to be the limit as h approaches 0 of 6 times x squared plus 2xh plus h squared minus 6x squared over h. Okay, and now we have a bit of cleaning up to do in the numerator. So we'll just distribute. So we're going to get 6x squared plus 12xh plus 6h squared, and then minus 6x squared over h. Okay, and then 6x squared minus 6x squared is 0x squared. So these terms kind of cancel out, which leaves us in the numerator with terms that have a factor of h in them, which is very convenient, because now we can factor that h out, right? So we're going to have a factor of h, and then we'll have 12x plus 6h over h. You could take the factor of 6 out, yes, but we don't. I mean, what we're really interested in is canceling the h. Yeah. Yeah. Okay. And then now what we have is something where we can sub in a 0 for h. 12x plus 6 times 0, and that's just 12x. Okay, so what is our derivative function? f prime of x equals 12x. Now we can plug in whatever x value we want, and we have the value of the derivative, or the value of the slope of the tangent line at that specific point, that specific value of x, of the function. Okay, so for example, which were the two that we wanted to find? F prime of 1 equals 12 times 1, which is 12. F prime of 2 is 12 times 2, which is 24. Okay, so when x equals 2, the slope of the tangent line is 24. Pretty steep. Pretty quick, pretty fast rate of change there. Okay, now this is pretty handy, this generalization, because this really speeds up that process that we did a few minutes ago. Okay, all right, so that was a quadratic function. Let's try this for a radical function. Okay, so here we have f of x equals the square root of x minus 3, where x is greater than 3. Okay, so find f prime of x, the derivative function f, the derivative of f of x. Okay, so we'll start out with f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, and by the way, this piece is on your formula sheet. Okay, and now we have to sub in to our function in this first piece an x plus h for x. So it's going to be the square root of x plus h minus 3 minus the square root of x minus 3 over h. Okay. So what do you think would be a useful thing to do at this point? Yeah. Yeah, conjugate. Multiply by the conjugate. Okay? So we're going to multiply by this conjugate. So that is the square root of x plus h minus 3 plus the square root of x minus 3 over the square root of x plus h minus 3 plus the square root of x minus 3. Okay? And in the numerator, we end up with this. So the first sort of radicand, right? The inside part is called the radicand. So x plus h minus 3 minus the second radicand, x minus 3, over this whole thing in the denominator, h times the square root of x plus h minus 3 plus the square root of x minus 3. Oh, I dropped the limit again. I don't know why I keep doing that. Don't do that, you guys. Some of you guys did that on the quiz. Don't drop this limit until you actually do the substitution. And then when you do the substitution, drop the limit. I'm not practicing what I preach. There we go. Okay. And now again, we have some tidying up to do in the numerator. So we're going to get the limit as h approaches 0 of x plus h minus 3 minus x plus 3 over h times the square root of x plus h minus 3 plus the square root of x minus 3. Okay, so now what do we have in our numerator? Yeah, just h, which is super nice. That's what we wanted. Because these cancel, and then I just have a 1 in the numerator. Okay, and now I can sub in a 0 for h. So I can drop my limit. 1 over the square root of x plus 0 minus 3 plus the square root of x minus 3. Okay, now when I sub in a 0 here, I actually get the same radical twice. So I have 2 of them. So my whole function, my derivative function is f prime of x equals 1 over 2 square root x minus 3.
And then do you not want to put that radical on top?
So if you put it on top, then you would actually have a negative exponent, because this is actually 1 over 2 times x minus 3 to the 1/2. F prime of x, okay? If you put it on top, then this exponent would become negative. It'd be to the negative 1/2. So it's actually better to keep it in the denominator and keep it positive. Okay? All right. So, say that again? Could you multiply, could you rationalize it? Yes, you could. No, you don't need to. I'm just trying to think, you know what? I'm trying to think, no. Don't rationalize it. Can we come back to that? I'm going to talk about that in a couple minutes. You wouldn't rationalize, let me think. If you rationalize it, you would multiply it by no, because it's going to interfere with where the derivative is defined. I'm going to come back to that. Okay? Good question, though. I'm just trying to think. If you multiplied by, yeah, you could. Actually, no. Yeah, you could. I'm thinking aloud. You could do that, but it's not necessary. Okay, now, notation. There's lots of different ways that we can notate derivatives. We've seen one of them, which is with sort of the little dash. That's a really common one. We say f prime of x. Sometimes if the function is y equals, we'll use y prime instead of f prime of x, right? So different ways that you'll see derivatives written. You'll see f prime of x. You'll see y prime. But this is one that's used a lot. And this is Leibniz's notation. And this one, dy dx, comes from change in y over change in x. Okay? This one comes from delta y over delta x. So the d is kind of like a delta, but instead of it being an average change in y over an average change in x, the dy over dx represents an infinitesimal change in y. So we're like, the change is so small that it's almost infinitely small. Okay, and that's how we sort of notate that the average, it's not, the rate of change is instantaneous as opposed to an average rate of change. Okay? So this becomes dy by dx when the rate of change changes from, using the word changes, average to instantaneous. Okay, and in fact, we're going to do a lot more on this later on in the unit when we actually break this up into a change in y versus a change in x. So this notation does become quite important. Okay? But these are all different ways that we can notate the same thing. We can call the derivative f prime of x, y prime, or dy by dx. Okay? Now, derivatives don't exist everywhere. Okay? So a function may be, firstly, if a function is not continuous everywhere, it's not going to be differentiable where there's a point of discontinuity. Okay? So that's one thing we need to know. Okay? If there's a point of discontinuity, there's not going to be a derivative there, because how can we find the slope of a tangent line at a point of discontinuity? Okay? A function is also not differentiable at the end point of a function. Okay? So actually, I'm going to come back to this example right now. This guy over here. So our original function was this. F of x equals the square root of x minus 3. Now, here we're given, actually, I should change this to that. F of x equals the square root of x minus 3. Okay? So let's think about this function and what it looks like and what the domain of that function is. Okay? If we're looking at f of x, it's a radical function. What is it going to look like? What does a radical function look like? Yeah. Yeah, it's kind of like half a parabola on its side. Where's the end point going to be? Yeah, where x equals 3. Okay, so this looks like that. Okay. Now, this is differentiable wherever f of x is continuous, except right here. Because we cannot, think about how you would create a tangent line there. It's an endpoint. You can't create a tangent line at that endpoint. So there is no derivative at that point. Now, if you look at the derivative function, right? If you tried to put a 3 in there, 1 over 2 square root of 3 minus 3, you're going to get 1 over 0. And you're going to get an undefined value. And so the derivative itself is undefined when x equals 3. So this guy has that domain. This one has this domain. Okay, so it's not differentiable. Differentiable means that there's a derivative there. The derivative exists there. You can create a tangent line there with a specific slope at x equals 3, which is the end point. Okay? Anywhere else where it's continuous and there's like a curve to it, the derivative will exist. Okay? And then, of course, it's not going to be differentiable when x is less than 3, because if x is less than 3, then the radicand will be negative, right? And then you also get something that's undefined. And that goes the same for the function as well. Okay? So that's one thing I wanted to talk about, and we're going to come back to that over here as well. Okay? So if we look at this function, we've seen this function before. F of x equals the absolute value of x. So this is one that is continuous. Okay. That's what f of x looks like. But again, like, how would you create a tangent line at this point? This is actually kind of like a V. There's a corner there. So what would the tangent line be? It's not curved, right? So it's not differentiable here. No derivative here. There's a corner on the graph. Now, we looked at this when we looked at limits as well, because when we looked at the limit of this function, well, actually, no, let's actually just look at, if we think about the slope of the tangent line in this direction, if you think of what's the slope of this line, this is the line y equals x, right? What is the slope of this linear function? 1, okay? This is the line y equals negative x. What's the slope of this function? Negative 1. So this is going to be what the derivative looks like. Not differentiable at 0. Okay, but basically you have a constant slope because it's a linear function. The slope doesn't change. The rate of change is always the same. It's just whatever the slope of the function is, which on the right-hand side, when x is positive, the slope is 1. And when x is negative, the slope is negative 1. Okay, but right here, there's no way of defining a slope. So we do not have a derivative at that point. Okay, in general, there's no derivative at endpoints, sharp corners, or any points of discontinuity. On f of x. Okay, so if there is any sort of endpoint, like we saw in the previous page, if there's any sort of corner like this, or wherever it's discontinuous, there's no way of getting a tangent line there. And so therefore, we're not going to be able to define the slope of the tangent line there. And so the derivative will not be defined in those locations. Okay. Now, I do want to add something in here that's actually not in your notes, but I want to talk about it briefly, which is just graphically how the two things relate. And we're going to do a much more in-depth look at this in our next unit, but I do just want to have sort of a brief on the surface look at this quickly. So what I want to do, did everyone get that down? Should I go back? Do you guys need more time? You're okay? Go back? Okay. Sorry. There we go. What I'm going to do is I'm going to graph a couple of graphs that I'm just going to make up. They'll be polynomial functions for now. And then I want to show you how you can use the graph of f of x to approximate the graph of the derivative by looking at the slopes of f of x and how they change. Similar to what we did here. All right, are we good? Are we good? Yeah? Okay. 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 So let's say that this is f of x. And what I'm going to do is I'm going to, underneath it, approximate f prime of x. And notice I don't have any scales on here. So this is a very sort of rough approximation. Okay? So when I'm doing this, the first thing I look for is if I were to draw some tangent lines in, where could I draw horizontal tangent lines? Where could I draw horizontal tangent lines? In what locations on the graph of f of x could I draw horizontal tangent lines? Those would be vertical, but horizontal. Yep. Yeah, the max mins, right? So the horizontal tangent lines would go on the max and the mins. Okay, so here, 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 here. What's that? Nope. Okay, so that's where the horizontal tangent lines are. What is the slope of a horizontal line? 0. So wherever the tangent line is horizontal, the slope, which is the value of the derivative, is 0. So what I'm going to do is I'm going to say, okay. There's a point at 0 there. There's a point at 0 there. There's a point at 0 there. And there's a point at 0 there. Okay, because remember, the derivative represents the slope of the tangent. horizontal lines have slopes of 0. Okay, the next thing I'm going to do is I'm going to look at the sine of the slope. I've kind of divided this into 1, 2, 3, 4, 5 chunks. I'm going to look at the sine of the slope in each chunk. So this piece over here, what's the sine of the slope here? If I'm sloping up to the right, yeah. Okay, then what happens in this section? Negative, 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 negative. Okay, then what happens here? Positive, 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 positive. What happens here? Negative, 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 and then positive. Okay, so I'm going to use these signs to tell me the sign of my derivative. Here, in this section, my derivative's positive. Then it's going to pass through 0 and go negative. Then it's going to be positive, negative, positive. Okay, because remember, the derivative is the value of my slope. So the slope here is positive. What I know is the derivative is positive. Here it's 0, then it moves to negative. Here it's 0, then it moves to positive. Here it's 0, then it moves to negative. And then here it's 0, and it moves up to positive. Does that make sense? Do you guys want to try another one? No? You got it?
And so then could you make f prime prime?
Yes. You absolutely can. So we're going to talk about second derivatives in our next unit. We could do that right now, though, if you wanted to. You want to? You want to do the second derivative? Sure. So that's f prime. Second derivative would be this. Let's do it in a different color. Oh, shoot. I went back to thick. F double prime of x. It's typically how we call it. Okay, now the problem with this, though, is that I wasn't being careful enough when I drew the first derivative. So actually, the values where the second derivative is 0 actually relate to something in the graph of f of x, and I wasn't being careful enough when I drew the first derivative so I'm hoping that it'll kind of work out. But again, I was being kind of sloppy, and I told you it was a rough sketch, so I wasn't planning on doing this, but hopefully I wasn't being that sloppy. We'll see. Okay, so let's see. We're going to see where this is 0, right? Horizontal tangent line there, there, there. Okay, so this is where my zeros are. Okay. What is the sign of that slope? Negative, then positive, then negative, then positive. So it goes negative, positive, negative, positive. Okay, let's actually see if that worked out. So where the zeros are should relate to the concavity of the graph. Not bad. Yeah, so what I mean by concavity is like a parabola, for example. This is concave down. This is concave up. Okay, when the second derivative is 0, and again, we're getting like about a month ahead of time, but where the second derivative is 0 is where the concavity switches. So you can see kind of here, right? That's concave down, and then from here to here, it's concave up. From here to here, it's concave down, and then from here to here, it's concave up. Can you guys see that? So if we look at our second derivative, This piece is concave down, which is why the second derivative is negative. This piece was concave up, which is why it's now positive. This piece was concave down, which is why the second derivative is negative. And then the rest of it is now concave up, which is why the second derivative is positive from there on.
So then could you technically skip the first derivative?
Well, so, okay, you could if you're only interested in concavity. Depends what you're interested in, right? So if you want to know where the slope, the first derivative actually tells you about your max min points in the original function, right? We're getting way, way ahead of ourselves right here, but if you think back to 20-1, for example, and you were looking at quadratic functions, you were doing like maximization problems, right? You had to like complete the square, you had to do all of this work to solve a maximization problem, to get the vertex, to get something into vertex form, to solve that problem, to figure out where the maximum point was on the graph, right? We don't have to do that anymore. We can just find the derivative, figure out where the derivative is 0, that's where our max point is. Because wherever there's a max or a min point, the derivative is equal to 0. So it depends what you're interested in. If all you're interested in is concavity, then yeah, you skip down to the second derivative. But if you're interested in where is what is the maximum value of this function or the minimum value of the function, then you want to use your first derivative, right? Yeah. Okay, so tangent is done. My tangent about tangent lines is done. So I'm going to stop the recording here.